So as I said in the previous video, this is an example of a proof where we could have used this term called without loss of generality. So I've written up here without loss of generality, and extremely often this is abbreviated WLOG, without loss of generality. And what is without loss of generality? Well, without loss of generality is a term that expresses that there exists some sort of symmetry inside of the theorem that you're trying to show, or some arbitrary naming of variables that doesn't actually matter. And so you can assume something about those variables. So let me go ahead and write down in detail what the definition of without loss of generality is. So whenever there is symmetry, and I'll talk about that in just a minute, or arbitrary naming of variables in the theorem that you're trying to prove, without loss of generality lets you do the following. So by claiming without loss of generality, this lets you fix different properties of your variables and hence reduce the number of cases that you have to consider. So for example, over here, when I was trying to show the theorem for integers m and n of opposite parity, show that their sum is odd, notice that m and n, those are arbitrary names. I didn't have to use them, right? I could have used p and q, or s and t, or I could have used n right here, and I could have used m right there. So here we have some arbitrary naming of variables. So because we have this arbitrary naming of variables, there's nothing special about them, I can reduce the number of cases that I have to consider by saying without loss of generality. So let's go ahead and see how this proof would change if I used without loss of generality. So first off, I'm going to have to erase the second case because it allows us to reduce the number of cases that we have to consider. So here, notice that I have completely eliminated case number 2. And I've completely eliminated that because instead of considering two different cases, one where m is even and n is odd, and the other case where m is odd and n is even, I can just say, without loss of generality, say m is even and n is odd. Because it's understood that the names m and n here are arbitrary. So this proof right here is going to work if you just replaced wherever you saw an m with an n and wherever you saw an n with an m. And so, since this proof is going to work, no matter how we name these m's or n's right here, I can say without loss of generality, let's just fix a property of the variables that m is even and n is odd. So it's understood by using without loss of generality that whatever proof that you use afterwards is also not going to be affected by you fixing this property that m is even and n is odd. So basically without loss of generality just means that I could take this entire thing, replace this m with n, and this n with m, and everything would work the same. And so it's just a convenient technique that allows us to reduce the number of cases that we have to consider. That's not the only place, though, that you can use without loss of generality. Because remember when I said symmetry over here? So let's look at another example where we could use without loss of generality. Let's say that we're considering variables x and y that are real numbers. And I want to show the triangle inequality, that the absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y. So let's carefully consider this. What I'm trying to show right here is this inequality. So I could call this my propositional function. So I could call this my propositional function xy. So what this example is actually asking me to show is the following. It's asking me to show for every real number, x and y, p of x and y. That is, this triangle inequality is satisfied. So notice something very special about this propositional function right here. There's some symmetry going on here. I can actually reverse this x and y, and the statement is the same. So let's go ahead and take a look. So if I were to take this, and I were to simply switch, instead of x and y, I now am looking at y and x, what do I get? Well, that is going to be the same thing as, well, wherever I saw an x, I'm now putting a y, and wherever I saw a y, I'm now putting an x. That would be the same thing as this inequality. And you notice this inequality right here is the exact same thing as that inequality. So I have some symmetry in the theorem that I'm trying to prove. My propositional function doesn't matter the order of this x and y. And that will allow me to then fix some property of these variables here. In particular, you could then start out a proof of this thing by claiming the following. You could start a proof by saying, without loss of generality, say x is less than or equal to y. Because x and y are real numbers right here, and since we have this symmetry and the propositional function that we're trying to prove doesn't care about the order of x and y, we can go ahead and fix the order of x and y and say that x is less than or equal to y. And that may reduce the number of cases that we would have to consider if we were trying to prove this triangle inequality right here using a proof by cases. So very importantly, whenever you try to use without loss of generality, you have to be absolutely sure that either you have an arbitrary naming of variables and your proof will work if you switch the variable names, or you have symmetry in your propositional function that allows you to then fix some property about them. In either of those two cases, you can use without loss of generality and simplify your proof.